Aerobatic pilots endure very high G-forces, while astronauts are trained to handle G-forces from any direction. But do you think you could withstand the G-forces experienced during a space launch? Hello Science Junkie, welcome to this channel. Today we'll examine the problems caused by G-forces in aerospace engineering. From acrobatic airplanes to space launches, G-forces appear anytime there is a change in speed. The clearest example, which we will all understand because we've all experienced it, is in a car that is standing still and suddenly accelerates. When the car accelerates, according to Newton's first law, your body and all your bones, organs, blood, and everything inside you tend to stay still. However, the seat behind you pushes them. That's what causes G-forces, which are usually not very high. Earth vehicles like cars, motorcycles, trains, and airplanes also lack significant acceleration. So the kind of G-forces you might feel aren't going to be very high, and they're definitely not going to be dangerous at all. For example, the fastest cars can reach 100 mph in about 2 seconds. A quick calculation using average acceleration over that distance gives about 1.7 Gs during acceleration. That's pretty insignificant if we start talking about the G-forces you experience in a plane during a maneuver. That's why things get interesting in aircraft. Here we experience the same G-forces forward and backward when the plane accelerates or brakes, plus upward G-forces in the longitudinal direction. These are the G-forces people mention when, for example, saying a pilot has endured many G-forces. They're referring to G-forces on the longitudinal axis, typically downward. Have you ever wondered why airplane G-forces are upward or downward? Let's use a fighter jet as an example. When it flies straight and then suddenly pulls up, G-forces are experienced. Look, we can see the plane flying straight, and suddenly when the pilot pulls the stick and the plane raises its nose upward, it enters a circular trajectory. Let me remind you that any circular motion requires a force to keep the object on its curved path instead of moving straight. According to Newton's first law of inertia, if there is no force acting on an object, that object will continue along its current path. And that's why, to maintain a circular trajectory, you need a force at all times that points toward the center. For example, when I spin an object on a rope, the rope exerts the force that constantly changes the object's velocity. The rope's tension acts as the centripetal force keeping the object spinning. In the case of the airplane, it's a bit more complicated because it's the airplane itself. By moving control surfaces like flaps, the tail elevator, or others. That causes the lift force to increase, and when the lift force increases suddenly, the airplane leaves its straight path and enters a circular path. Inside the airplane, your forward inertia remains, so the seat pushes against you, causing you to change direction. The force the seat exerts on you is the G-force you feel. Interestingly, every particle in your body, bones, muscles, organs, and fluids like blood also has inertia. This force moves through your bones and muscles to the rest of your body. And they turn quickly. But your blood, a fluid in your body, still has inertia. The blood senses the centrifugal force and shifts to the curve's outer edge. Here you can see how blood flows to your feet. And this is what we call a positive G-force maneuver, because the blood tends to go down as your body expects. For example, as I stand here, my blood is pulled downward by gravity. So that's typical. We were made for this. That's why positive G-force. In the case of doing a maneuver where you withstand 3 positive Gs, every particle in my body would weigh 3 times more. For example, at aviator school, they took me flying and we did a maneuver to try it. 0 G. What's interesting isn't the 0 G itself, but what happened right before. The maneuver goes like this. The plane flies straight, then abruptly lifts its nose, causing G-forces to spike to around 4. And then came the fun part with the free fall. But look, for example, was my face really like that during the part where we were experiencing about 4 Gs? We're talking about 4 Gs, which almost anyone can handle easily. Look at my face. I can't imagine 9 Gs. That must be incredible. I remember I couldn't think of anything. It was only 2 seconds. But in that moment, all you think about is just being there and getting through it as quickly as possible. You can breathe, and that's it. And I also remember during the turns when I was turning with the plane, how we were just holding on there, nothing else. It was about 2 Gs, and I couldn't move my legs. I looked at them, tried to move, thinking, we're taking 2 Gs, but I couldn't. Because suddenly your leg feels twice as heavy. Your brain doesn't send enough signals to your leg to move double the weight. I guess if you get used to it, eventually you can move your leg, obviously, and it's no big deal. Since it was my first attempt, I couldn't do it. If we turn now with your head on the curbs outside, centrifugal force would send all the blood to your head. That's what we know as negative G-force. A negative G-force maneuver is one where the blood goes to your head. Humans tolerate positive G-forces better because we're accustomed to blood flowing downward. Negative G-forces are quite low, around 3 to 4. Can you handle that? However, it's known that humans can withstand up to 6 or 7 positive G-forces. 7 is already quite a lot. Actually, anything above 7 starts to cause a lot of problems. And that's why, when designing a general aviation aircraft, for example, it's made to withstand about 5 or 6 positive Gs, but no more than 3 negative Gs. Because it's known that the aircraft will never be in those conditions, basically because the pilot wouldn't be able to withstand it. Here you feel negative G-forces as the seatbelt holds you while making the turn. Your inertia pushes you outward, but the seatbelt holds you, so all your particles try to move outward. The seatbelt holds you, causing you to feel those forces. G in the case that the seatbelt comes undone, you would keep going straight, you would leave the circular path, and you wouldn't feel G forces. And now let's talk about 0G, because there's usually a huge misunderstanding when we talk about 0G. This literally means that you are in free fall. To help you understand, 0G always means that if you put a scale under you and it reads 0, you are in free fall. For example, when I was in the cabin with everything floating, a scale under me wouldn't register anything because we were all weightless. Now, with all this, we can understand the G-forces in this maneuver. It involves quickly lifting the plane's nose, then pushing the pedal fully to turn and descend. First, tilt the plane's nose upward during this maneuver. You experience around 4 positive Gs, then free fall repeatedly, and after recovering, there's another peak of about 3.5 Gs. There's another thing to emphasize, and that's that G-forces in airplanes are governed by the classic equation for centripetal force, which goes with the square of the speed. R is the curve's radius, and since 5 is squared, speed is the key factor in the equation. So, with some fighter jets flying at around 2,000 kilometers per hour, if they were to trace a small turn, they'll feel strong G-forces since speed is squared and they're moving fast. You should also know gravity always pulls downward. So if a fighter jet, for example, does a loop, the person flying has the ground right below them. You'll need to add a G, which is Earth's own G. However, if you do it the other way around, with the pilot's head pointing toward the ground, then you'll have to subtract 1 G to know what the pilot is actually enduring. Now we can really relate this to space launches, since those truly include a bit of everything. During the launch process, the rocket keeps accelerating, the whole time. You feel downward G-force, and as the rocket turns, you continue to experience it. Because of turning, just like airplanes, after reaching space and the engines shut off, you'll feel 0G. We'll discuss later why this happens in space. What happens is there no gravity there? That's a topic for another video, but for this one, it's important to understand that in space, you're literally experiencing free fall. And then, at the moment when the spacecraft is about to enter the Earth, during re-entry, you would experience G-forces from braking, since the spacecraft is going very fast, and the atmosphere slows the spacecraft with strong resistance. But for example, if we stop to think about the Starship for instance, it's very interesting to notice that when it turns around and the rockets are activated to slow the spacecraft down to 0 speed. There, a lot of G-forces will be endured, because the rocket will keep going down, but there will be a rocket generating a lot of force upwards. And that of course will cause a lot of acceleration to be endured inside the rocket. I find it really interesting regarding this topic to realize the limits of G-forces, the limits of technology. In aircraft, it's now more about human limits than technology setting the boundaries. For example, a fighter jet can handle up to 9 positive G-forces. It's not built for more since no pilot could handle it, so it makes no sense. It could be done, but what's the point if the person inside might faint or die? I tried to show this in my Starship critique video, but it seems people missed the point. Starship's technology is fantastic. The problem is the people inside, the people who go inside. Passengers likely aren't ready for those forces. Gee, there's something interesting about this, but I don't know if it's true. I've read and heard about it from various sources online, so it might be true, but I haven't seen anything official, so don't believe it yet. But they said that the Eurofighter didn't get a thrust vectoring nozzle because this would exceed the pilot's limits, and that's why the Eurofighter, for example, doesn't have a vectoring nozzle. I'm not sure that's true. I hope you enjoyed this video. It was very thorough, especially about forces. Gee, if you enjoyed this, give it a like. There's one thing before finishing the video that I haven't mentioned. But I've started a channel in English, more or less like what I do here, but I intend for it to be higher quality, in English. Well, for those of you who want to learn English, or who are studying your degree in English, or simply if you know English, well, you can check it out. I'll also leave the link below. Well, actually, I'll leave the link here so you can see it. Here's a link to subscribe to my channel if you haven't yet. As always, science comes first.